Hello there, young students of chemistry. This is a short little recording about metallic bonding theory and the evidence that we have to support it. So first of all, metallic bonding is not a true chemical bond. So we're not talking about a bond as in an ionic or a covalent bond. We're simply talking about an attraction between atoms of metals. So I hate to really use the word bond, but it is an interparticle attraction, the particle of one metal attracting to the particle of another metal. And so you can see here that this occurs between atoms of the same metal. So if we have aluminum foil, right, all of those aluminum atoms that are in the foil are attracted to each other through a metallic bond. And this also occurs when we have alloys. Alloys are mixtures, and they are mixtures of elements or compounds, at least one of which would be a metal. So this is how metallic bonds form. We have all of these metals, and as we know from our conductivity demonstration, electrons in metals can leave their atom. And that's exactly what happens. But it's not all of the electrons in the atom, it's just the valence electrons. So the valence electrons leave their atom, and they kind of all group together into this one just clump of electrons. So we know that when electrons leave an atom, that creates an ion, and that is a positively charged ion. And we know that things that are positive are attracted to things that are negative. So what happens is these electrons will form this, what they call sea of electrons. So all these valence electrons just kind of float around the positive metal ions. So remember that we practice active note taking. So read what we have here and write what you need to write. I want you to pay attention to the word delocalized. We know that if something is delocalized, that means it has been moved from its original position. So the valence electrons are delocalized from their atom, and they create this sea of electrons, and you'll often hear it referred to as a sea of electrons. So the electrons are moving all over, and they are attracting the now positive ions of the metals. So take a minute to read and write. Pause where appropriate. So the actual attraction, as I said, is between the metal positive ion, which we know is a cation, and the sea of electrons. So you can imagine that the more core electrons a metal has, kind of blocking it from the sea of valence electrons, the less attraction it's going to be, and therefore the lower the melting point and boiling point, because those metals are more easily broken away from their other metals. So really large atoms like gold and other metals that are down there have lower melting points than things that are much, much smaller and have a stronger attraction to the sea of electrons. Another thing that will indicate how strong the metallic attraction is the number of valence electrons that the atom produces. So if you consider a sodium atom, its electron configuration ends in S1. That one electron leaves its atom and becomes part of the sea of delocalized electrons, and then that sodium ion now has a positive 1 charge. And you can imagine that if we have magnesium, which loses 2 electrons, or aluminum, which loses 3 electrons, we've got more electrons in the sea, and we have a more highly charged ion, a positive 3 or a positive 2 versus a positive 1. And when you have these charges that are greater charges, they're going to be more strongly attracted to the negative charges, which are the electrons. So this little diagram kind of shows you the sea of moving electrons. I don't know why that little glitch is in there. It didn't used to be there. But they're showing these positive ions and that purple moving goop is the sea of valence electrons that the metals have donated to that the electrons have delocalized from. So that purple kind of moving thing is the sea of electrons. And this is really good theory for explaining why metals will conduct, because we know that when something conducts, we have electrons that are moving, and we know with metals are conductive. So those electrons leave their atom and then just float between all the other atoms. It also explains why metals are malleable and ductile. If you remember that malleability is the ability to hammer a metal into a flat sheet or to shape it without it breaking. So anytime a little crack would occur if the ions are separating from each other, what's going to happen is the electrons are going to fill in that crack and kind of keep the atoms together. And that's why the atoms don't just break apart and crumble into this brittle powder. And it also explains why the metals are ductile. We know that ductile means that we can take that piece of metal and we can pull it into a wire, and it just keeps getting thinner and thinner and thinner without breaking. Again, if there's any little cracks, the electrons are going to fill in those cracks and attract the atoms and keep those positive metal ions from breaking apart. So that's metallic bonding theory. Let's take a minute to talk a little bit about alloys. So alloys are solutions, just like sweet tea is a solution. It's a mixture that is the same throughout. It doesn't mean it has a definite composition, but it is every sample of that mixture is the same. You might be familiar with some common alloys. I don't know if you've ever seen a cast iron frying pan, those really heavy black frying pans our grandparents used, or my grandparents used. They're great for cooking. Bronze is another common alloy that we use. We tend to make statuary out of that. And then we have things like gold jewelry. Now, when I say gold, I mean the alloy of gold. And mostly we use that for jewelry. Okay? So if we consider cast iron has two things in it. It has carbon, which is a nonmetal, and then it has iron in it. The thing about a cast iron pan is that these were used back before we had things like gas stoves and electric stoves, and people were cooking on fire. So, like an open pit fire. So what they needed was something that would get really hot and then stay hot. So carbon has a very high specific heat capacity, meaning it can store heat really well. Carbon's a decent little insulator. However, if it's going to conduct heat to cook something, it needs to also have the metal in it. And the metal is going to provide that transfer of energy. So iron is in it to provide the transfer of energy. Carbon is in the alloy to keep that pan hot once it absorbs all that energy, because people back then couldn't keep fires going all the time. It was consuming too much wood. So we'd have that carbon element, and the carbon contributes a high specific heat capacity to the alloy. We're going to talk more about specific heat capacity later. But for our purposes now, what I want you to understand is that the properties of the elements that are in the alloy are combining to make the properties of the alloy. And of course, the iron contributes the element of heat conductivity to the pan. And if you've ever looked at a cast iron skillet, they are a really deep, rich black color, and that's because carbon as an atom is a deep, rich black color. So if we consider bronze, we usually use that for statuary. We do have a very famous statue in this country that is not made of bronze, but is made of copper, and copper is one of the components of the alloy bronze. And that is the Statue of Liberty, and we all know that the Statue of Liberty is green. Well, copper is a really kind of shiny, lustrous metal, and it's a reddish brown in color. It is not green. So if we consider what's on the outside of that statue, what we have is that it has rusted. That is oxidation. The compound is actually copper 2 oxide. And what happens is the copper is reacting with the moisture in the air and the oxygen in the air and producing this copper 2 oxide rust. If you are an artsy person, you may have called that patina. Lots of art people like to call that patina. It's just rust, but that certainly is a prettier name for the word rust. And then bronze has another component, which is tin. So here's the thing. When we make statuary and things out of that we're going to display, most metals are like that shiny kind of gray color. Well, there's only two metals that are not that shiny gray color in their metallic state, and that is copper and gold. So what happens is we want this beautiful color, but we don't want the copper to rust and turn green, so we make the alloy bronze. And bronze statuary can stay in the elements for a long time and still not rust. So we have these metals that are very easily moldable. Copper provides that pretty color that we want, and tin provides a resistance to rust. And of course, the more copper we have in our alloy mixture, the more likely it is to rust, and also the kind of redder, browner the color. The more tin we add, the shinier it's going to be. It's going to be really brightly colored. Now, gold jewelry is made of alloys, and in gold jewelry, it's not just gold. There's some silver, there's some copper. There are some other things. They keep alloying more and more things in our gold because we want something that's stronger and that's going to last. And here's the thing about gold. Gold by itself is really soft, and that is a negative thing. So what we want is the color of the gold without the softness of the gold. Because when you think about things like rings that you're going to wear on your finger or bracelets, we use our hands and our arms a lot. If you have just pure gold on there, it's likely to bend and break. So we want to alloy that gold and make it a little bit stronger, and that's what these other components are for. They're to add strength to our gold jewelry. And you're probably familiar with the carat ratings. Carat is just a percentage. Carat is, as a unit of weight. It's a very small unit of weight, certainly not as small as an atomic mass unit, but not nearly as big as a gram. And the reason we use carats is because we need to know how much is there, but a gram is just too much weight. So we're talking about carat weights. Things that are measured in carat weights are gold, platinum, diamonds. Tell us how heavy they are in carats. So when we have jewelry that is labeled 24 karat jewelry, what we're really saying there is 24 carats. And yes, it's spelled K-A-R-A-T, but it's abbreviated with a capital K. Out of 24 carats of the mixture. So it's 24 carats of gold for every 24 carats of the mixture. Well, we know that 24 out of 24 is 100%. So 24 karat is really just another way of saying, hey, that's pure gold. It's very soft. It will break very easily. Often 24 karat gold jewelry is reserved for things like earrings. We don't bang our earrings around on countertops and stuff like that very much, so it's less likely to break. 18 karat gold would be 18 carats of gold for every 24 carats of the mixture of the alloy. And we know that 18 divided by 24 is 75%. So 75% of 18 karat gold is gold. The other 25 are some of these other components. And as I said, we're alloying more different things, it seems like, all the time. 14 karat gold is great for things like rings and bracelets. Maybe you could get away with an 18 karat gold necklace and it wouldn't break. But again, that's 14 carats of gold for every 24 carats of the mixture or the alloy, right? And we know that 14 24s is around 58%. And then, of course, gold, and you'll notice if you ever look at 24 karat gold, or heck, even 18 karat gold compared to 10 karat gold, 10 karat gold has less of that gold color. It is shinier than 14 karat gold, but it's very strong. So we can use 10 karat gold for rings, stuff that's going to get banged around a lot and we don't want it to break. So that would be 10 carats of gold for every 24 carats of the alloy. And we know that that is about 42% gold. So in your lab, the brass penny lab, you're going to make an alloy, and that alloy is brass. You're going to use a copper penny, one of them that has a lot of copper in it, one that has a little bit, and some zinc, and mix those together to make the alloy brass.